In this comprehensive briefing, we are bypassing mechanical failure points entirely, from quantum-scale molecular water filtration to friction-free plasma power generation and dual-band gap tandem solar architectures. This is the definitive blueprint for next-generation energy capture and future materials. Global water scarcity isn't a supply problem, it's a filtration bottleneck. In 2026, molecular engineering is turning ocean water into fresh drinking water with zero friction. Traditional desalination is an environmental disaster. It relies on massive thermal distillation plants that guzzle fossil fuels and dump toxic, hypersalty brine back into our marine ecosystems. To scale clean water under National Science Foundation, NSF energy directives, we are deploying atom-thick material barriers. Graphene oxide membranes reject salt ions on a quantum scale. The secret is precise sub-nanometer sieving. These graphene sheets are drilled with microscopic pores smaller than a single hydrated sodium ion. Water molecules glide through with near zero friction, while salts are mechanically blocked. By stabilizing these membranes against swelling, we get a system that operates at a fraction of the pressure of standard reverse osmosis. It purifies brackish industrial waste and ocean water effortlessly, leaving us with completely pure H2O while keeping operational energy costs functionally zero. Traditional livestock farming is a highly inefficient energy loop. In 2026, bioreactors are decoupling protein synthesis from animal slaughter entirely. To get 1 single calorie of beef, a cow must consume over 25 calories of grain. It's a thermodynamic failure that wastes vast land tracts, uses trillions of gallons of water, and drives global emissions. Under strict EPA bioefficiency standards, we are shifting to cellular agriculture. Cultivated meat facilities bypass the animal's organs entirely, directing nutrients straight to target tissue cells. The engineering relies on cellular proliferation. Animal stem cells are placed in an optimized plant-based nutrient broth inside massive bioreactors. They divide rapidly, attaching to structured edible scaffolds that mimic real muscle fiber tissue. Because these facilities utilize vertical space and recycle 90% of their water, they require up to 95% less land than traditional ranches. The entire system is powered by co-located renewable grids, producing pure, sterile protein at a fraction of the thermodynamic cost. Your clothing is a wasted, energetic surface area. In 2026, next-gen materials are transforming ordinary fabrics into wearable, kinetic power plants. We are completely dependent on rigid, toxic lithium batteries to power our portable personal tech. These devices require constant grid charging and create millions of tons of unrecyclable electronic waste every single year. To capture wasted kinetic energy under NSF nanotechnology frameworks, engineers are developing smart textiles. By weaving Triboelectric nanogenerators directly into yarn, we turn friction into electricity. The core tech utilizes contact electrification. When two distinct polymer fiber layers touch and separate during normal human movement, electrons are forced to transfer, creating a continuous electrical current inside the clothing. These energy-harvesting textiles are completely breathable, flexible, and washable. They seamlessly charge biosensors, communication arrays, and personal devices without a single external plug, turning everyday human movement into an active, independent power grid. Mechanical turbines are the weakest link in power generation. In 2026, fluid dynamics are bypassing moving parts completely to generate friction-free electricity. Standard power plants rely on spinning metal turbine blades to convert heat into kinetic energy. These moving parts suffer from extreme friction, mechanical wear, and massive thermal losses that cap overall efficiency. Under NREL high-temperature power cycles, we are deploying magnetohydrodynamic systems. Instead of spinning a solid copper wire through a magnetic field, we push an ultra-hot, conductive gas fluid through it. The science relies on the Lorentz force. When an ionized gas or liquid metal fluid rushes through a powerful magnetic field, the positive ions and negative electrons are forced to split toward opposite electrodes, creating a direct electrical current. With zero moving parts to break or wear down, MHD generators operate at extreme temperatures, where standard turbines would melt. They integrate directly with geothermal or modular nuclear sources, extracting raw electric power directly from moving fluids with zero carbon emissions. standard silicon solar panels have officially hit a physical wall. In 2026, a synthetic crystal material is breaking through the absolute limits of clean energy harvest. Commercial silicon panels are mathematically capped at around 29% efficiency due to the Shockley-Quasar limit. They absorb the red spectrum of sunlight well, but completely waste high-energy blue photons as heat. To maximize solar capture under strict NREL testing protocols, engineers are stacking materials. Enter perovskite tandem solar cells. We are printing thin layers of synthetic crystal directly on top of traditional silicon bases. The secret is dual-band gap spectrum harvesting. The top perovskite layer catches high-energy blue and green light waves, while the bottom silicon layer absorbs the remaining low-energy red and infrared waves. No photon is wasted. By stabilizing these perovskite crystals against moisture and heat degradation, we push panel efficiency past an unprecedented 35%. This design generates more electricity per square meter, drastically reducing installation footprints and shattering the theoretical limits of solar power conversion forever. Follow Lumix.HQ for your daily dose of positive news.